So once we have seen what could be the 1D picture of the material, let's extend that to the general case. And now we are doing abstraction and generalizing. We have to respect the rules that we have established for this kind of constitutive models, okay? But we'll try to generalize in this setting the model. So this is the uniaxial case that we have explained so far. Let's generalize that to multi-axial cases, multidimensional cases, 3D cases. The vector, the tensor of stresses, the apparent stresses, external stresses, are proportional to what would be the corresponding effective stresses. So the stresses that would the material carry, assuming that it's elastic. So the stresses that the elastic material in 3D would sustain if the material was elastic was the product of the 4-order elastic constitutive tensor times epsilon, where this is a tensor that could have, for instance, the format that we have seen for isotropic elasticity, depending on the 2 parameters and blah, 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 blah. Okay? Times the reduction factor 1 minus d, where d is again one scalar variable that takes the value between 0 and 1. So this is what we call the effective stresses, and then we'll say again that the stresses are equal to the apparent stresses are equal to the effective stresses multiplied by a reduction factor that is evolving along time. This reduction factor having the same restrictions that we have seen for the 1D cases. D dot is greater than 0. So the damage always increases, never decreases. At most, it remains stationary. And the damage value ranges from 0 for no damage, in which then this term is 1, to 1, in which this term is 0 and the stresses are completely released. Okay, so simple as this. Okay, I will see that I will show that this is not enough. You have to just complement that with some additional, but the concept is already here. Okay? So let's now use what we have learned so far. This way, this approach, this inclusion of our constitutive equation in this thermodynamic framework that we have visited in these past 2 classes. So first, let's consider a strain-driven problem, which is the most appropriate, I insist, for the type of finite element approaches that we are going to use when we insert this constitutive equation into a finite element problem, linear general solid mechanics problem. So the free variable set is just 1, the strains. We could have also chosen the stresses, but we choose the strain because it's more convenient. 1 free stresses. That means that this variable can, what does that mean? That it's a free variable. What is the implication of that? What is the implication of that? Any value, any variation, any rate, any change, okay? Can take any value, in principle, maybe any. The most important is that for any value, for any instantaneous value, it can evolve in any way. Okay, then let's consider the set of internal variables, and let's consider that we have just one internal variable. Let's call it R, okay? And let's assume, as we said, that we need an evolution equation. We'll talk about that later on, but let's assume that this evolution equation will have the format of R dot being a function of the strains. The instantaneous evolution of the internal variable is a scalar function, let's call it lambda, of the strain itself and the value of the internal variable itself, instantaneous values. Okay? We'll talk about that. And then the remaining variables are dependent. That means that they are function of the strains, the internal, the free and internal variables. So we talk about the stresses, we talk about the apparent stresses, the one that I observe macroscopically, that are a function of epsilon r, the free energy function of epsilon r, for instance, the damage variable, which is a variable that is going to play a role here. So that should be a function of epsilon r, okay, and so on. Well, now remember what was the next ingredient was assuming a free energy. Okay? So let's assume a free energy which is that one. Let's call phi 0 the free energy that we would consider for a purely elastic material. Okay, you remember that for linear elastic materials, that free energy had the form of 1/2, it's a quadratic form in terms of the strains, 1/2 epsilon c epsilon. Okay? Then it's rather natural to consider that as the material damage, this is the capacity, tells about the capacity of a storage of energy in terms of the sustained strains. Okay? But then we affect that capacity of storage of energy of the material by the factor 1 minus d. We can see that when d is equal 1, that means completely broken material, there is no capacity to store anything. But for d equals 0, then we have the capacity, the same capacity as any elastic material. So let's try this kind of definition of the free energy. It's just the one that we would have in elastic material multiplied by the factor 1 minus d. Okay? Okay, then at a certain point I will need the free energy. Now I will forget the term rho 0 that we have used so far. So free energy this is rho 0 phi, so to speak, is the free energy per unit of volume. Okay, already. If not, it was the specific free energy, I would need to place a rho 0 in front every time I use it. So I just keep that. And then phi would be a function of epsilon r. Phi dot would be, evidently, the derivative of phi with respect to epsilon times epsilon dot plus derivative of phi with respect to d. Well, I should consider r, but look, the way I've chosen that is that phi depends on r through d. Okay, so well, for convenience, I can place that derivative of phi with respect to d times d dot, but in turn, d dot depends on r. Okay, we'll see how. Okay, so now let's talk about dissipation. So we are covering what we learned before. The dissipation, that neglecting thermal effects, has this form: the sigma times epsilon dot, the stress power, minus phi dot, the stored energy. That means the power per unit of time and unit of volume that is entered into the material minus phi dot, which is the energy stored in the material per unit of time and unit of volume. And that has to be greater than 0 for any epsilon. Never forget this. That's what the second principle of thermodynamics says. So now I replace sigma times epsilon, is this term here. Phi dot will have a first part, looking back at what we have seen here, the derivative of phi with respect to epsilon times epsilon dot, which is, what is it? Here, the derivative of phi with respect to epsilon times epsilon dot. And then this second term here, that one, which is the derivative of phi with respect to d times d dot. The derivative of phi with respect to d times d dot, and that has to be greater than 0 for any epsilon dot. Okay? And then, now let's consider that phi is a function of, is that function 1 minus d times phi 0, which is the elastic free energy, and this returns the continuum damage model free energy, and we use the Coleman's method. In fact, by the evolution equation, this part doesn't depend on the evolutions of anything, and finally, this part here, since epsilon dot is any, has to be 0. So finally, we recover the universal form of the constitutive equation. The stresses are always the derivative of the free energy with respect to strains. That's universal. Okay? By the way, the free energy is that. What is the derivative of the free energy with respect to? The free energy depends on epsilon and r. But this part depends on r, so depending on epsilon, it's just this part here. When I take the derivative with respect to epsilon, these two cancels because I'm taking twice derivative. Finally, this is 1 minus d, this is not affected, times c times epsilon. Okay? So that's returning what we're looking for. The constitutive equation that we had just in the generalization of the constitutive equation. The effective stresses, sigma epsilon c times epsilon, multiplied by a reduction function which is 1 minus d, d being the damage function, which is going to be determined. Okay? And what remains if this term cancels? What remains here is this part here. So dissipation is minus the derivative of phi with respect to d times d dot. But if you look at phi, where is phi? Phi is here. What is the derivative of phi? Looking at that expression. The derivative of phi with respect to d is minus phi 0. Okay? And phi 0 is the elastic free energy. Okay? So finally, dissipation is phi 0 times d dot. Okay? Look, phi 0 is a quadratic form of epsilon. This is always positive. Okay? Because this is a positive definite. It can be proven for elastic materials. This is positive definite. So this is always a positive result, a positive value. So phi 0 is always greater than 0. So we find that the equation of dissipation says that phi 0 being positive, or 0, times d dot is greater than 0. So that we can conclude that d dot is greater than 0. What is it saying? If I had started with that model, with no previous approach as I did, that would say something that now we can interpret, we can understand as a consequence of my approach, but otherwise it just would be abstractly that d dot, the evolution damage of the damage variable, is always positive, never negative. Which now can be translated into the fact that if that d dot was negative, that would mean that the material could experience self-healing. Okay? So this, again, is something that's going to be a common fact in our approaches. The second principles of the thermodynamics will place always restrictions on our constitutive model, as we saw, for instance, in the little examples that we did in the past class, restrictions on the, you remember the restrictions that appeared always on the viscosity, for instance. Okay, the viscosity had always to be positive, and so on. Here is saying that the damage variable, the evolution of the damage variable has always to be positive. Well, I mean, and that proves how useful is this approach, because otherwise it would be very difficult to, even in more complicated models, to place such a type of restrictions. Okay? Well, we need more things. This is the basis, the fundamentals are here. But now we need more ingredients in order to model what we look. So I little by little, I will try to introduce them. So far you have followed it, I think so. Have you gone very slowly? You have understood? Okay. So now we're going to define some norms. You know what a norm is, no? Norm is a measure of the distance. Okay? The Euclidean norm, if I want to measure a distance of 2 points in an Euclidean space from point X to point Y, or the distance of the origin to a certain point here, I have to take the norm of the vector that joins both points, okay? And we take what we call the Euclidean norm, which is the product of X times the identity times X. The square root of this, which is the square root, by the way, this is X, so that the square root of X times X, which is that distance. Distance is the square root of X. That's what we call the Euclidean norm, okay? But it can be a norm if instead of 1, I place here any positive definite matrix, okay? And of course, by the way, the locus of points having the same distance to that, in this metric, in the unit matrix, in the unit metric here, what is the locus of points in Euclidean space having the same distance in the Euclidean matrix to the origin of coordinates? What is? What? In 3D, a sphere. Okay? And a sphere. Okay? Now imagine that instead of that, I take another matrix. For instance, a matrix that is not the unity. For instance, a matrix that is A0, 0B. For instance, A being greater than 0. I could do it. Okay? And I could take the distance in this matrix, let's make the matrix the matrix A, of point x and point 0 as square root of x times A times x. And that I would obtain something different. Okay? The number I would obtain is not exactly this d, it would be a different. And this will depend probably, unlike in this previous case, I cannot just translate that in x times x. This plays a role anyway, so probably I would obtain something that would be an ellipsoid centered into the origin. The points having the same distance measured in this non-Euclidean matrix would be now an ellipsoid. Okay? Follow me? Okay, that can be extended also not to vectors but also to tensors. And we can talk of metrics and distances which are always scalars, but in a space in which the elements of the space are not vectors, distances between this point, which can be expressed in a vector, and another point, but in terms of tensors. Okay? Okay, so that this introduction done, we are going to consider the stress space. Maybe you are already familiar with the so-called high Westergaard or stress space. Are you? Have you been told about this in the continuum mechanics course? I think so. You should. Anyway, you know, talking about the stresses, just a little reminder. Talking about the stresses in fact define a space of how many dimensions? The stress tensor in general is symmetric. So we have, in principle, this would be in three-dimensional case a 9, 3 times 3, 9 numbers, but due to the symmetry there are only 6. But then we can see that any stress tensor can be diagonalized. Okay? And this diagonalization provides what we call the principal stresses and the principal directions. This can be done always, and these principal stresses can be proven to be always positive whenever the second order tensor, which is a stress, is symmetric. Okay? So, something that you should know. From any stress tensor, there is a unique set of 3 values which are the principal stresses. Okay? And then we can play around that a lot. But for now, for us, we just take these principal stresses, and there is always one, the larger, one, the smaller, and one, the intermediate. We order that. Stresses, those stresses, in this order. That's what we call the order in continuum mechanics. Other disciplines, like for instance soil mechanics, use another order, but this doesn't make a large difference. But for us, let's consider that. So, any stress state that we have in a solid, if I just take a solid and I just produce some strains and I have some stresses, I have to take one point of this solid and the stresses that at this time this point has. From this, I can compute the principal stresses, which is computed using a diagonalization process and so on, eigenvector problem. So I take the 3 eigenvalues, which are called the 3 principal stresses, and I order them into the order sigma 1 is the larger, sigma 3 is the smaller, sigma 2 is the intermediate. Okay? And I can do that for all the stresses. Okay? So I have for every point, one set of 3 vectors. And then I consider one Cartesian space in which the x, the axis x is associated to sigma 1, the axis y is associated to sigma 2, the axis z is associated to sigma 3. And then this stress state, which is characterized by the 3 principal stresses. If I consider in this space, this corresponds to one point in this space. Okay? So finally, if I consider all possible stress states, I would fill this space of points. Okay? Everyone giving the 3 principal stresses corresponding to the stress state I consider. Well, I wouldn't fill it completely. Why? Because of this restriction. This restriction makes that I'm working just in one sector. Okay? Because I can never find sigma 1 smaller than sigma 3 because I'm just ordering that in that way. So anyway, that's something that you should know. And by the way, I think that in plasticity, in what you have given in continuum mechanics, probably you have been taught about it. Okay. So, this is what is called the stress space, the high Westergaard stress space, in which every point is characterized, the coordinates of every point define the three principal stresses, or the stress state of which point is representative of. By the way, this could be done also on the stresses. Every second-order tensor is amenable to create a similar three-dimensional state. Okay, so we could talk, and we will talk of the strain space as the one obtained by the principal strains characterizing the strain state of every point, etc. Okay, so representative points of this space is what is called a straight line that passes through 0 to the origin, which is characterized by the three coordinates being the same. This is the bisectrix of the first sector. You know, any system like that divides the space in how many sectors? How many? 8, right? 4th in the upper part, 4th in the lower part. Okay. First one is the one that having x, y, and z greater than 0. Okay. The second would be x greater than 0, y greater than 0, z smaller than 0, etc. Okay. So the bisectrix of this space, sigma 1, sigma 2, sigma 3, is a straight line passing to the center of this, okay? And it's called the hydrostatic axis. It's called that because the water at rest, is typically sustaining just pressure states characterized by the three principal stresses being equal and negative, by the way. So living in these water stress states, water at rest stress states would be living at. Okay, anyway, so now consider the high Westergaard stress state. Let's consider now a point of that, which is represented by this sigma, and then let's consider a matrix like that, which is now, instead of a second order tensor, is a fourth order tensor, which is positive definite, so this product is always positive. So we can define this as a scalar, and this scalar can be take the square root, and this return a result that we will term the distance from the origin to that point is just a measure of the distance from the origin to a given point of this space in the matrix M. If the matrix M is the unit tensor, then we will talk about a Euclidean distance. Okay, but if it's not, we can talk about non-Euclidean matrix and non-Euclidean distance. We can talk about a distance and a norm of the stresses, a measure of how large are the stresses. In the same way that in that point, a larger distance means larger difference, larger matrix means a larger distance. Also here, a larger matrix means a larger value. It's just a scalar that returns the magnitude of the stresses measured in terms of this matrix. Okay? Okay. Now, we will use a family of matrices like that, the fourth order tensor like that, which is, by the way, isotropic. Remember, I told you that all the isotropic fourth order tensors can be described in terms of two scalars. And that is, by the way, what characterizes the elastic constitutive tensor belongs to this family. Alpha and mu being the Lamé coefficients. But of course, there are many others. But now you understand that I'm anticipating something. Okay? So let's consider matrix like that, characterized by this tensor, alpha plus beta greater than 0 and beta greater than 0. And then this matrix, of course, it can be proven that if these conditions are fulfilled, this is a positive definite fourth-order tensor, this matrix is always a positive, this product is always a positive number, and so you can take the square root, and this provides a measure of the magnitude of this stress, which is always positive. So it doesn't distinguish if it's large in this side or on that side. It just measures what is the distance of every point to the origin. Okay? So we'll use for our problems metrics for the stresses, and that would be in a scalar, and we'll call tau sigma, a scalar that measures the magnitude of the stresses in the high Westergaard space. Okay. Look, by the way, if you take this matrix, then it can be proven that what we will obtain here, the locus of point having the same magnitude, the same distance to the origin, is not a sphere, as it would be if alpha and beta are 1, or rather, if alpha is equal beta, 0, beta equal 1, but is an ellipsoid of semi-axis. So it looks like that. It's an ellipsoid, one of whose axes is the hydrostatic axis, and the other two are the orthogonal ones. Okay. We can talk about then strain norms though. So now the strain norms will be taken in that way. We'll define the strain norm as the norm of the effective stresses. Look, the effective stresses depend on the strains. Why? Because are defined as C times epsilon. The definition of the effective stresses is C times epsilon. So by taking the same norm, but now instead of the apparent stresses, we use the effective stresses, we'll obtain by some operation sigma m sigma bar by replacing here epsilon c m c. This c star, let's call this product a fourth order tensor, which is c star. So that's the norm of the strains in another matrix, which is, by the way, the m times the matrix is mc mc. But again, it can be proven that this is another matrix that measures in a different way if we want, but measures how big, how large is the strains, are the strains in the corresponding strain space, which again is a strain, is in a space, a three-dimensional space, in which we take the first principal strain, the second principal strain, and the third principal strain for every strain state, and then this is the hydrostatic axis for this space. Look that whenever, for instance, a property of a matrix is that matrix, it's only zero, if that matrix is zero, only if the strains are zero. That's a property of any matrix. A matrix, to be considered a matrix, has to fulfill this property, that when the matrix is zero, the distance is zero, that means that the point is right here. So the point is zero. Okay. Okay. Yeah. Yeah, so this product can be proven to be a fourth order tensor. I mean, just do the operation. Just contract two indices. There are four indices here. Okay? And then when we contract with that, two of them are mute. When we contract double contraction with that, two of them are mute. So all the indices of that are becoming mute. And only it remains talking indices, only the two first of these and two first of these. So we have four talking indices, which is a four order matrix. That's something that it's out of the, I said that these kind of things you should be aware of, or believe me. Okay. Okay, so now we have defined a matrix that measures in terms of this M, but transformed by this equation, with C star matrix, that defines the amount of a strain that we have at every point.